All right, let's take a look at the back of our team test. We've got a graph, nice, continuous, smooth graph. The figure above shows the graph of f prime. Again, I would probably circle that right away. The derivative of a twice differentiable function, f, on the closed interval. So front and back, we're kind of talking about this word differentiable, and that means it has a derivative. It's smooth and continuous. On the closed interval from 0 to 8, closed interval. The graph of f prime has a horizontal tangent lines at x equals 1, we can see. X equals 3, we can see. X equals 5, we can see. The areas of the regions between the graph of f prime and the x-axis are labeled in the figure. The function is defined for all real numbers and satisfies f of 8 equals 4. All right, we read the question. Find all values of x on the open interval from 0 to 8 for which the function has a local minimum, and justify. So this is our derivative, and we want to find when the function would have a local minimum. So minimums look like this. And what I would describe is that for a function to have a minimum, it has to be decreasing and then increasing, meaning its derivative has to go from positive, or from negative to positive. Does that happen? We have the derivative. This is the derivative. Does it ever go from being negative to being positive? And the answer is yes. Happens right there. These numbers are all negative down here. The derivative is negative down there, and it crosses and goes to being positive. Therefore, the only local minimum would be at x equals, I think that's 5, 6. And the justification would be the derivative went from being negative to positive. F prime of 5 is less than 0, negative. F prime of 7 is greater than 0. The derivative has gone from being negative to being positive, and that's my justification. All right, now I've made a note to adjust this for next year. In order for you to do your B, determine the absolute minimum value, and then concave down and increasing, I think it might be more beneficial for you to do D first, using the axes above, graph f of x. Maybe we should even do that first. So let's do that now. We're going to do our part D, and then we'll come back to part B and C. So graph it. So the first thing I want to discuss is that f of 8 equals 4. So at 8, my value should be 4. That's an absolute must-have in your graph. F of 8 must equal 4. Now, we've been practicing graphing derivatives from functions. So now we're talking about graphing a function from a derivative. And we did this in a team. This function, or this derivative, is positive from here to here. That means it's increasing. We already discussed that this is a minimum, so I need a minimum somewhere around here. Now we don't know where that is unless we talk about the areas. The areas are important here. Areas of derivatives tell us y values of functions. So I think once I say this word, we're going to kind of understand. If this area is 7, the function has gained 7. Its displacement was 7. So if it got to 4, where was it before that in order to get to 4? It had to be at -3. Does that make sense? If I'm at -3 and I gain 7, I get to 4. Similarly here, this area would have lost 3. So in order to lose 3 to get to -3, right here, I would have to be at 0. 0 minus 3 gets me to -3. So let's keep working backwards. I gained an area of 6 to get to 0, so now I should be at 1, 2, 3, 4, 5, 6. And I gained an area of 2 to get to -6, so here I am at -8. Now, the graphs I looked at had a general shape like this. We should have a very steep slope here to a 0 slope here, down to a 0 slope here, but we stay increasing until we have our maximum here at 0, back down to our minimum here at -3, and then up. Anything like that is totally acceptable. That would have got us 3 out of 3. You got a 2 out of 3 if you had that general shape, but you didn't have the exact points based on f of 8 equals 4. So now that we've got that graph, let's talk about B and C. All right, now that we've got it graphed, we want to determine the absolute minimum value of f on the closed interval from 0 to 8 and justify. So we've got it graphed, and clearly we can see that the absolute minimum is when x equals 0. And a lot of people answered and were pretty good with their thinking of, well, the minimum is when x equals 0. But the whole what was the value was required as far as saying the y value is -8 is the minimum value. The justification we're looking for here is to check extrema and endpoints. I would make sure I had that written down. That's very important. The extrema we did have a minimum at x equals 6, but its minimum value was y equals -3. So that's not it. And then our endpoints. At x equals 0, we are at -8. At x equals 8, we are at y equals 4. So our absolute minimum value for justification would be at -8. And that would be all the justification we need. And teams said things like, well, all these derivative values are positive, so the function keeps increasing. Those are also very good words to say in your justification. And then finally, on what open intervals contained from 0 to 8 is the graph both concave down and increasing? Explain. Well, let's get out some highlighters and talk about increasing. Where is the graph of f increasing? Anywhere its derivative is above the x-axis. The function is increasing. Now, let's talk about where's the function concave down. The function is concave down when the derivative is decreasing. So maybe I should write those words out. Functions concave down when derivative is decreasing. So where's that? The derivative is decreasing here. The derivative is decreasing here. So there it is. We just found it. It is concave down and increasing from 0 to 1 and from 3 to 4. That would be the open intervals. And I made them open with my parentheses. We can kind of see that here. Let's take a look. Increasing, concave down. And then increasing, concave down. I think I can really kind of see that. The other thing we can kind of learn from this problem is that when this had a 0, or a 0 slope, right here should be a point of inflection. 0 slope, point of inflection, and 0 slope, point of inflection. So I should have 1, 2, 3 points of inflection. Keep mathing it up.